there, and welcome to our tutorial on Unit 7, Lesson 1, Investigation 1. This is our first investigation and lesson of our recursive and iteration unit. We'll learn about what those words mean later, but essentially what we're going to deal with is a fish population where we have some fish dying, we have some fish being added by us, and a rate at which these are dying. So you've looked at probably populations with exponential growth, maybe exponential decay, but this might be a little different situation, especially on how we calculate it and the graphs of those. So I really want you to try to think about the situation to talk about what are some factors that we have to worry about with these fish, how could you estimate the current fish population, and what would you want to know to find out the long-term population. So here's our specific relationship that we're going to have. We're going to have 3,000 initial fish in our pond. We're always going to add 1,000 fish at the end of the year, but over the year the population decreases by 20% by taking deaths, natural deaths, anything like birth and things like that. So in number one, I want you to try number one actually to finish. I would probably skip B, but for especially A, C, and D, I would stop the video, look through these, see if you can actually calculate. Now I'll say one assumption that we are making is the 20% we're going to take or multiply first before we add that 1,000 fish. So I would stop it here, write your now next, and see if you can find the next year's or next couple years population, and then see if you can use your calculator to find a bunch of those populations. All right, hopefully you've tried that. If not, I will write that now next for you, which it should be next equals. I'm always going to take that 20% first. So since I'm losing 20% in my calculation, I'm going to remain or have 80% remaining times my population at that time plus 1,000, starting at 3,000 fish. If you look on your calculator, what that'll look like is this calculation here. 3,000 times 0.8 plus 1,000, you should get 3,400 fish. Now, the investigation wanted you to use that answer feature on your calculator, so just press times 0.8 plus 1,000, and if you notice, you can keep pressing enter, and it gives you every single year past that. Now, in a table, we're not going to make a function for this actually right away. So what I've done is actually made some tables for you in the next couple slides. But eventually, if you notice, just keep clicking, and something actually interesting happens. And what should happen is that fish population should actually level off. And we haven't seen that before. So I would want you to find where that actually levels off, and that's what we'll talk about tomorrow in class. But let's see what we can actually change in our situation. If you have found, or keep clicking, this should level off at 5,000 fish. Okay, it keeps increasing, but eventually it gets to 5,000 and it just keeps going over and over and over. The explanation of that, just think about what 20% of 5,000 is. Okay, 20% of 5,000 is 4,000 fish, so then I add 1,000, I'm back to 5,000. So it just loops over and over. So I wonder if in my, let's say this is a business situation, maybe I change the initial population of the fish. Maybe I want to start with fewer fish and see if I can get to 5,000. Maybe I just want to make it really big and just have a whole bunch of fish and let them breed and have babies. So let's see what actually happens. Now I have a table here of the values all starting at different values. So you notice year one, different values. So what I did is made a table of values for this. Here's year 2, here's year 3, and here's year 4, and here's year 5. And as you notice, the 3,000 is increasing. The 1,000 is decreasing very quickly. The 10,000 is actually decreasing. Now if I go 10 years later, you can notice 20 years, 30 years, and if I go to 70 years, they all level off at the same spot that they did when we started with 3,000. So in fact, we have our first relationship that we're going to talk about. If I change the initial population, the level off remains the same. That's a very important thing that you would probably want to have in your notes. If we're dealing with these situations where we're multiplying by a rate, adding something, if you change the initial population, you can start anywhere, and if you keep these two values the same, the level off remains the same. All right, so let's think about, there's two other things we can change. We just change the level off at the same point. We can change the rate and the restock. Let's look at the restock. Okay. So some values that I picked, you know, before I was adding 1,000 fish, now I'm going to add 500 fish, maybe 2,000 and 4,000. So let's look at the table of values for those. Start at the same spot, start at 3,000. There's year 2, year 3, year 4, and year 5. So notice this one's actually decreasing. This one's still increasing. This one's still increasing pretty quickly. If I go 10, 20, and 30, these all level off. So if you look past these 30 years, eventually they'll level off. And this one's at 2,500. This one's at 10,000. And this one's at 20,000. Our initial level off was 5,000. So I wonder if there's a relationship with that. When we added 1,000, we got to 5,000. When we added 500, we got to 2,500. So that's almost like we restocked half as much. 2,000, we actually doubled our restock, and look what happened. We quadrupled our restock, and look what happened. Hopefully you start to see the pattern that if you actually change the restock rate, the relationship is a direct relationship. If I increase one, the other one increases. And here's the notes I would take for this situation, that if I take some scale factor or I multiply the restock by something, in this case I multiply by half, look, the level off is half. Multiply by 2, the level off is 2. So that's our relationship for that. The last thing we can change is the decrease rate, or sometimes we call it the death rate. It depends on the situation, but we'll have like insulin and other situations where we'll have a decrease rate. So initially it was a 20% decrease, but we used 0.8. So what I did is, well, I really made the fish die at 80% death from this one, 60%, and this is probably more realistic, about 10% death. But then I showed you the decimals that I used in those equations. So if you notice, fish population, all the same at the beginning. The ones that had a lot of death go down pretty quickly. I mean, this one, the restock really had an effect. It was actually going up. So as you notice, some are going down, some are starting to level off right away. And in fact, this 80% death levels off at 1250 pretty quickly. So does this one. Now this one takes a long time to level off, which is fine, but it does eventually level off at 10,000. So look what I did here to get to that 80% death. Before I was at 20%, so I actually quadrupled the death rate. I was killing lots of fish. And eventually got to 80%. And look where the level off was. Initially it was at 5,000. And then it went to 1250. So think if there's a relationship between 5,000 and 1250. This one I tripled the death rate. So I did times 3, and then look at this relationship, see how much bigger it is. And then this one I multiplied by half. I actually only did 10%, and then I leveled off at 10,000. So hopefully you can see this relation. What happens is when I quadrupled it, this level off is a fourth of where it was before. When I multiplied the death rate by 3, it was a third of where it was. Multiplied by 2 was, or sorry, multiplied by half, it actually doubles it. So if you change the decrease rate, what actually happens is we call it an inverse proportional relationship. What that means is, I mean, just like we had direct, we have an inverse proportional relationship. That proportional word is important. And here's essentially the relationship we get for this. If I multiply by something, some number to the decrease rate, times 4, times 3, times 1/2, it's always going to be 1 over k as big for the level off. So that's that inverse proportional relationship. So to conclude, there's a lot of relationships we just talked about. We could change 3 things. We could change the initial population. We could change the restock. We could change the death rate or decrease rate. So that's a lot of stuff to remember. So I wonder if there's an end-all equation that can find me the level off. Where is this going to level off? Maybe if I change how many fish I start with, or change the death rate, maybe change 2 things, can I find the level off quickly? And that's what I want you to come with tomorrow. I'm going to leave you hanging a little bit. There is a level off equation. And, the 2 things you have to change are restock, decrease rate. Now you can change the initial population, but as we saw, this one doesn't matter as much. If you start anywhere and these remain the same, it actually still levels off the same spot. So think if there's a relationship between these 2 values that you can always find the level off quickly. Rather than clicking your calculator tens of thousands of times, just say, you know what, if I do this calculation, that's the level off. So hopefully this helps. We'll review in class, see if we, or make sure we know these 3 relationships, and then this final level off magic equation. Hope this helps. See you later.